by Larson. It's automated conjecturing for proof discovery.
Thanks. So I'm going to tell you about a new application for an automated conjecturing program that I wrote with Nico Van Cleemput. He's a postdoc at Ghent University. He's at a computational graph theory group that does amazing things with graph generation and things like this. So the things I want to do in this talk are tell you a new idea how to use this conjecturing program. So by the way, there's two versions of the program. One makes conjectured relations between invariants for any kinds of mathematical objects. The other makes conjectured relations between properties for any kinds of mathematical objects. We have a paper, the first paper about the program just came out, and that's on the invariant relations version. There's two more papers that are coming out. One is an application to making conjecture for Chomp, which is a combinatorial game, and then there's the paper about property relations. And so I don't have time to tell you that much about the program. I'm just going to tell you about the newest application that we're thinking about. And that's generating sketches of proofs or proof ideas. And an application that I want to talk about is something called the friendship theorem. You might not remember what that is, or maybe you've never seen it. I'll tell it to you at the appropriate time. Let me tell you, my abstract is a little bit of a bait and switch.
It always is, not just for you, but for
I saw the conference announced on the abstract deadline on maybe DMAnet, and I wrote up something based on what I was thinking about at the time. And I'm a graph theorist, and so it was about some property that we were investigating of graphs. And I thought, well, this isn't a strictly graph theoretic audience. I'll try and talk about something friendlier. All right. So mostly I'm not going to tell you how the program works. What we do is we have a bunch of syntactic inputs, and we make expressions of increasingly large complexity. And then we test if these expressions are true for a bunch of objects in the mathematical domain that we're working in. And then we test if the expressions are significant with respect to some previously stored expressions. That's the main heuristic. The heuristic idea is from Shimon Feitlovich, who wrote a program in the 80s called Graffiti. This belongs to a body of work that goes back to the 50s, with beginning with Hao Wang at IBM, and includes people like Pierre Hansen and Gilles Caparossi at HEC. And so there's this area of research. The idea here is the one from Graffiti. And for anything that you want to make conjectures about, what you need to do is give the program some example objects. If you want invariant relation conjectures, you need to tell the program some invariants for those objects. By invariants here, I mean numbers, computable numbers associated with those objects, or properties of those objects. And then what you'll do is you'll choose one of those invariants, and you'll ask for conjectured upper or lower bounds for that invariant. Or if you're investigating a property, you'll ask for conjectured necessary or sufficient conditions for that property. So our program is open source. It's all on the web. It has a nice GitHub page that I'll show you in a second. It's written for Sage. I've heard a few people use Sage here, so that's good. Maybe some of you don't know what Sage is, but it's a program like Maple or Mathematica. It has Python as its interface language, and Python is a super friendly language. For some of my early papers, I wrote C code in order to investigate things, and I'm not a great C programmer, and so eventually I'd spend more time hunting down C bugs, usually related with mallocs and things like this. Instead of thinking about mathematics, Python is a great mathematical prototyping language, and hopefully I never have to malloc again. Sage has lots of nice stuff built into it. It's got Gap and R, and GLPK is the default linear programming solver, but if you have a Gurobi license, you could just pop that in and it works. It's got a semi-definite programming solver, other nice stuff. You can get all of your output in LaTeX, including, for instance, I'm a graph theorist, so if a graph comes up, I can just write LaTeX parentheses graph, and it'll give me nice TIPS code that I can put in my papers. And it's got lots of graph theory built in. It's got lots of predefined graphs and predefined invariants and properties and graph constructors. It has some of the constructors from this Ghent group, including Buckygen, the Fullering constructor, benzene, the benzenoid constructor, Plantree, the planar graph constructor.
You're talking about Sage or about your program?
No, Sage. This is all, yeah. Sage has all of these things built in now. Naughty, by the way. So Brendan had his own personal license, and just this year, so you had to manually install Naughty, but now it's included in Sage. Brendan was more flexible with his license, so that's nice. And this community is growing, so it's kind of fun. All right, here is our webpage for the program. If anybody wants to play around with it, Nico's written a nice thing here to get you going quickly, including examples. All right, so here's a graph property. Pairs have unique common neighbor. That's how I've named the property in the program. And this is the property that for the graph, any pair of vertices have a unique common neighbor. Okay? So here's an example of such a graph. So if you look at any pair of vertices, say one of the outside ones and the center, it's got a vertex that's a neighbor of both of them, and it has exactly one. If you look at two of the outside vertices, they have a unique common neighbor. So the center guy will be the common neighbor in that case. We call these flowers. Other people call them windmills or fans. This class of graphs where you've got a vertex in the center surrounded by triangles. Okay. All right, now in this first experiment, what I want to do is generate sufficient conditions, conjectures for a graph having the property that every pair of vertices has a unique common neighbor. There's a variety of databases. In the main database, there's only 164 graphs, so this might seem kind of small to you, but these are graphs that were from the literature. They're Peterson graph and things like this, some snarks, things that were counterexamples to previously made conjectures. Whenever we make a conjecture and we discover a counterexample, we put that into the main database. We think these are examples that are significant in some sense. One of my dreams is to eventually have all the graphs that have ever appeared in the graph theory literature, but that's not a one-man project. But whenever I read a graph theory paper and I see a new graph that I haven't seen before, I rip out the page and I stick it into a big folder of things that I mean to code in the future. And it only has 87 properties in it right now. One of the things that we wanted to do here is, so in the first paper, we wanted to demonstrate that the program can make conjectures in a variety of domains. So the paper has number theory conjectures, graph theory conjectures, combinatorial game conjectures, and matrix theory conjectures. And now what we want to do is, we're both graph theorists, so now we want to demonstrate that programs like this can really be useful in exploring graph theory. So now we're just focused on the graph theory portion of the program. we're adding all of the invariants and properties and graphs that we can find. So, so maybe at ACMES 3, this will be a much bigger number. If there is an ACMES 3, I didn't know there was an ACMES 1, but now the conjecture expressions are going to involve these properties, and there's 5 propositional operators in there right now, these standard ones, and, or, implication, not, and exclusive, or. And this is, so Sage you can run locally, you can run it on your big cluster. It also has a nice web interface. If say Rob and I wanted to start on a project right now and Rob didn't have a Sage account, he could set one up in a second. It doesn't cost any money, and it neat things that we could share a project and get going, and you'd end up with a window that looks like this. And so here it says property, and here it says I'm defining the property that I want to investigate, that the pairs have all the pairs of vertices have a unique common neighbor. And here is the actual call to the program, property-based conjecture, and you need to tell it some number of objects, that's what graph objects here is, some number of properties. These are names of lists of graphs and lists of properties. The property that you want to investigate, and here it says sufficient equals true. So that means I want to run sufficient condition conjectures for my property. If I wrote sufficient equals false, that would mean I want necessary condition conjectures. And here, one of the things about this main database is we've pre-computed all of the invariants and properties. This is, so Nico just visited me, and this is a feature that we just added to the program. Previously, the program would recompute all of the invariants and properties every single time it ran, which was okay if your graph objects were only small graphs. But now we have bigger graphs in there, and if you have even a graph in with more than 100 vertices, one of the properties is being Hamiltonian, and you might know that that's an NP-complete property of graphs. And so you'd sit there waiting for conjectures, and behind the scenes it's recomputing whether or not some graph is Hamiltonian. So now the advantage here is you get the conjectures instantly because it has all the data pre-computed behind the scenes. And when you run the conjectures, you get exactly these 2 conjectures. So the first one says, if the graph is not triangle-free and it's a cycle, then all the different pairs, each pair of distinct vertices has a unique common neighbor. And so this one, it might amuse you, being not triangle-free and is a cycle. Well, there's only one graph that has that property, namely the cycle on 3 vertices, the triangle. And so this is actually a true conjecture, because for the cycle on 3 vertices, it is true that for every pair of vertices, there's a unique common neighbor. And then the second says if the graph is not a split graph, so the non-graph theorists don't need to know what this means, and it has a star center. Now this term will come up again. A star center is a vertex that's adjacent to all of the others, like in the flower. So if it's not a split graph and it has one of these vertices, then every pair of vertices has a unique common neighbor. Okay? Now, the conjectures that the program produces, they're going to be true for all of the input objects, whatever you have in that list of graphs. And the way that the Dalmatian heuristic works is that it only makes conjectures if they're not implied, if they say something significant. That is, they're not implied by any of the previous conjectures. So that means there's got to be some object in the database where the conjecture says something that the previous conjectures didn't say. Okay? Now, last year we added a new feature to the program, the ability to add what we call theory. What had happened was we sent Barry Mazur some of the number theory conjectures, and he was interested in conjectures that weren't implied by any of the theory and the number theory literature. Well, there's no way for us to know that, but we did add a feature so that a user could add these things. So in particular, in the example that we saw, we know that is K3 means the graph is a triangle. We know that if the graph is a triangle, then it's going to have this pairs property. So now you could say that's theoretical knowledge. What you'd want is, if you're generating sufficient conditions, you could think of the graphs that have property P, there's some circle, and sufficient conditions are smaller circles, and what you want to do is make more and more sufficient conditions so that union of those circles eventually fills up the P region. So if you have this as theory, it won't make a conjecture that's just true for graphs in that circle or the union of things that you have in that theory list. So it's got to add at least one more graph or one more object to the union of those conditions. So now we have this theory, we're running property-based conjectures, we have the same list of graphs, same list of properties. The property that we're interested in is that the pairs have a unique common neighbor. Now we have this theory parameter, and you run conjectures again, and you get a single conjecture. It says that if the graph is Eulerian, which I'll talk about later, if the graph is planar, it can be embedded on the plane without any crossing lines. If it's a Galilei tree, an interesting thing here, and an interesting thing that can happen to you, is that the program can make conjectures where if you didn't know what the words mean when you put it in the property list, you get conjectures that are necessarily surprising. I put in being a Galilei tree only because it was already built into Sage. It was easy for me to add in this list. I may not have even ever looked up what those words mean, but when it appeared in this conjecture, well, then I had to go and figure out what a Galilei tree means. I'll tell you later. So if a graph has all three of these properties, then every pair of vertices has this unique common neighbor. And it only made one conjecture, which means this conjecture is true for every single graph in the database. Okay? So that's an example of a sufficient condition conjecture. So now here's our new idea. We want to investigate an implication. We want to investigate the statement that if a graph has property P, then it has property Q. So the graphs that have property P are a circle. If this is true, the graphs that have property Q are possibly a bigger circle, but definitely the P circle will be contained in the Q circle. The program is going to make some number of conjectures of necessary conditions, and if you include the necessary condition into your theory, what that means is the program is going to keep running. So the program keeps running until it can't make any better conjectures. It's going to keep running until the intersection of that property and the intersection with the conjectured necessary conditions is equal to the class of graphs that have property P, at least with respect to the database. So here's the main idea. You want to prove an implication. You run the program. It's going to make some necessary condition conjectures like C1 and C2. And because of the way that the program is designed, what it means is the intersection of the graphs that have property C1 and C2 and property Q are actually going to equal P with respect to the graphs in the database. And what that means is the intersection of the graphs with property C1 and property C2 have to be in the collection of graphs with property Q. What that means is it gives you a proof sketch. So this is a conjecture. We don't know that it's actually true. It's only true for the objects in the database. Only true for the objects in the database, only true for the objects in the database. But if you could prove all three of these statements, it would imply that if a graph has property P, then it has property Q. So that's our idea. That's the main idea. And now I'll tell you an example. So the friendship theorem says this. It says if you have some people, and every pair of people have the property that they have a unique friend in common. So maybe Rob and Dave have Ilya in common, and so on. It doesn't have to be the same person. And Wendy and Patrick have me in common, but just one in common. Okay, then there has to be a person that's friends with them all. That's what the theorem says. And the graph theoretic interpretation is if you have a graph that has the property where every pair of vertices has a unique common neighbor, then there has to be some vertex that's adjacent to them all. That is, has a star center in the lingo of the program. Right? And so here's one of those graphs. Every pair of vertices has a unique common neighbor, and this graph indeed has a star center. Okay. Now, oh, by the way, I didn't mention, so this is a result of Erdos, Renier, and Soch from the 60s. The proof is in Proofs from the Book. Those of you that know this, it's very short and clever, and but the proof does involve some use of eigenvalues. And so while it's in the book, you couldn't explain it to your mom without a lot of background information. So I thought this might be a good candidate for making up an example for others. Maybe we could, maybe the program would give some ideas that don't run through eigenvalues.
So you're assuming no mums are mathematicians?
No, my mom.
Okay.
So in this 1966 paper, they immediately, everybody sees this, you can't have 4 cycles. Vertices 1 and 3, if you had a 4 cycle, they've got 2 guides in common. So that already violates the condition. Okay. Now, we haven't run conjectures yet. So this is what I want to investigate. And we've got this pairs property, implies that the graph has a vertex that's adjacent to all of the others. So in our investigation, I'm going to use this as the property, and this is my cue, having a star center, that's the theory, and then I get conjectures. These are the only 3 conjectures that it makes. It says 3 things. If the graph has this pairs property, then it's Eulerian, then it's circular planar or outer planar, and it's a Galley tree, which I still haven't told you what that is. But if you could prove these 3 things, and that the intersection of these properties is contained in having the property of having a star center, you've got a new proof of the friendship theorem. Okay? So an Eulerian graph is one where you can trace all of the edges exactly once and get back to where you started. Okay? The Euler's criterion is that you have this property if and only if the degrees are all, it's connected and the degrees are all even. And it turns out that you can prove this. I'm running out of time, unbelievably, or believably, or I'm used to it. But you can prove that. Circular planar or outer planar means that the graph can be embedded in the plane and all of the vertices are contained in some face. Here it's the outer face. Okay? The main idea here is a theorem of Harari and Chartrand that says a graph is outer planar if and only if it doesn't contain a K4 or a K23. A K4 is the complete graph on four vertices, and a K23 is the complete bipartite graph with 2 on one side and 3 on the other. And you can see that if you had a K4, you don't have this pairs property. Here's 2 guys that don't have a single neighbor in common. You have 2. Here's 2 guys that don't have a single neighbor in common. They have 3. And so this is the main idea here. That's that the Harari-Chartrand condition says you can't have a subdivision. So there's more to prove, but this is central. This is what a Galley tree looks like. These are graphs where the blocks, the maximal 2 connected areas are either complete graphs or they're odd cycles. Okay? Now it turns out that that this can be proved. I'm going to scroll through this. I'm going to skip all the ideas, but I think the slides are going to be posted, or you could talk to me. But this can also be proved. If you know those three things, you can prove that the graph has a star center. I'm also going to skip the proof ideas, because it's not even the main purpose of the talk, but it's just illustrative. Now, we didn't fully prove the second conjecture, that if the pairs of vertices have a unique common neighbor, then the graph is outer planar. We only made some observations based on the Chartrand-Harari theorem. So let's suppose you're stuck proving one of the lemmas. What can you do? You can rerun this kind of investigation using your new Q as the theory and generating new conjectures, and then you get some help in trying to prove the lemma. So that's something you could do. And our new project, so right now there's these 164 graphs with pre-computed data. We have 145 other graphs that are important in the sense that they came from the literature and they were counterexamples to previous conjectures where we don't know the whole story, like whether or not they're Hamiltonian. So they're in a separate database. There's 87 properties, there's 78 invariants. All the properties and invariants in these graphs they're all on GitHub if anybody wants to participate in our project of increasing Sage's graph theory knowledge. It's easy to do. An interesting thing is that the way that the program works, it makes the syntactically least complex statements in order, makes them of larger and larger complexity. And what that means is that a human couldn't, it's not the case that there could have been something simpler that the program missed, because it does it in order. So with respect to the properties that the program knows, there can't be the properties that the program knows and the propositional operators that are in there. A human couldn't have made a conjecture that was simpler with respect to complexity defined in this way. And this is the last slide. So this is my dream, is to publish is to code all the published invariant graph theory, invariance properties, and examples. It'd be a huge project, not as big as OEIS, because that's all the math, and this is just graph theory. But what you get are conjectures that are guaranteed to be true for every example that has ever appeared in the graph theory literature, and the simplest conjectures involving published concepts. And that's it. This is the web page I showed you before. This is our graph invariance project web page, and this is the first paper to come out of this. That's my email address, and thanks for your attention.